No questions? You're all good? Good. So stay active on the forums, help each other out. Don't be afraid to share code. There's no, with this game, with this assignment, there's no problem. Just don't, take your friend's video game and submit it as your own as well, because of all the assignments, this will be the easiest one to catch that kind of bad behavior. People tend to remember if they've played the same video game before. Okay, so last class, there we are. We were working on binary search. So we had studied big O notation, and we were convinced that we were going to make this efficient algorithm for searching in a sorted array called binary search. We had a good plan for it, so ignore that code down there. We had a plan for what we wanted to do. We're given a sorted array. We're going to do this recursively. If the length of the array is 0, then certainly we're not going to find what we're looking for in there. Otherwise, we take the middle of the array, the middle index m. We check if the thing we're looking for is less than m. If so, we recurse on the first half of the array. If the thing we're looking for is bigger than m, we recurse on the second half of the array. And if it's not less than or bigger than, it must be equal to, so then we just return true. And we've implemented this and tested it. It was working well. Hard to tell if it was working fast or not, because we had nothing really to compare it to. So we just decided to analyze it by hand, actually just inspect the code rather than run it to see how fast it is. And we saw where there's going to be a problem. And that's right here when we try and make this recursive call and we say, let's recurse on the first half of A, or let's recurse on the second half of A. Well, the way we did that was we took A and we grabbed a slice of it that contained everything in the first half, or a slice that contained everything in the second half. And that's when we realized this is going nowhere, because that means we're copying half the elements of A. If we're going to copy half the elements, we might as well have just walked through all of the elements looking for the value x that we're looking for. That would probably be faster. So what we wanted was a way to do this recursion. Keep going with this idea, but not having to copy half the elements of A to do the recursion. And the way we do those things is, this is something that comes up a lot. So when you want to implement solutions recursively, it often happens that you need to define an extra function, one that takes more arguments than you would expect it to. So for example, to make an efficient recursive version of binary search, I actually want some auxiliary function. Let's call it, I don't know, bin search. And we'll put an R at the end to say that that's the recursive one. So it takes an argument A, and it takes two indices. And those, it takes two indices, which are the place to start the search, so the index, to start searching at, and the number of elements beyond that index to continue the search. So in this case, we're interested in A starting at position 0 and going all the way up to the length of the array, and we'll look for x. Okay. So it takes an A, it takes an index I, it takes a n, x, and the comment should x is in the sorted sequence A at I, A up to I plus n. Okay, so it's somehow a more specified function that says don't look in all of A, only look between starting at I and up to position I plus n, or I plus n minus 1. Okay. So that's what we do, and then the standard binary search just calls that function saying, well, actually look at all of A. It's only when we call it recursively that we'll do something different. So now we need to change things. So before we were checking if the length of A is equal to 0 and saying if that's the case we'll return false. So now we're supposed to look only in this subarray A at I up to AI plus n. So what's the equivalent thing of asking if the length of that is equal to 0? Not if I equals n, because this goes up to I plus n, but if I equals I plus n, which means n equals 0. Okay. So if n equals 0, so n here is substituting for the length of the array that we're searching on, at least the part of the array that we're searching in. So if n equals 0, then we return false. Otherwise, we want the middle part of this array, the middle location in this array. So we'll say m is n over 2. So rather than the length of the array over 2. And now we want to know, so what we have is, I guess we could just quickly draw it. We have this array A that's given as input. We have some index I that refers to a particular element in A. And we're only supposed to look up to index I plus n, actually minus 1. So, right, this is index I plus 0 all the way up to I plus n minus 1. That's n numbers there, or n array locations there. And so what we did was we took m is equal to n over 2, which means that here the middle of this array is I plus m. That's the location that we're interested in there. So we want to compare x, the thing we're looking for, to the middle position in this array. So if x is less than a at I plus m, we'll have to recursively search. If x is bigger than a at I plus m, we'll have to recursively search. And if otherwise it's equal to, then we actually can return true. So we want to call bin search. We're not slicing anymore. We're actually just going to take the array. So this says, at this point, if x is less than a at I plus m, we would like to continue our search on this subarray here, right? So if x is smaller than this thing, then if x is smaller than this value, then it must be over here or it's not there at all. So we want to continue on this range. So that's the array that starts at position I and actually has length m. Yep.
This is assuming that the array is sorted, right?
Yes. Yes. All of this is only works for sorted arrays. Okay. So this is bin search starting at position I on the subarray that starts at position I and has length m. Okay? And otherwise, we want to look in the second part of the subarray. Well, that second part of the subarray starts here, this is position I plus m plus 1. And the length of this thing is n minus m minus 1. That's this length here. N minus m minus 1. Okay. Let's check if this works. It's very easy to confuse your indices here. So I prepared this before class. If I remembered it correctly, it'll work. If I didn't, I have it written down here so I can correct it. Okay. So I want to do A is equal to a range maybe 100. There's A, it's sorted, so we can use it. And I want to call binary search A, maybe with the value 33. Didn't return anything. Because we forgot to return something here. Okay, A is equal to range 100. Binary search A, let's look for 33. Miss the Y. Binary search. So it says true. 34, 35, that's all true. If I look for 35.2, it says that it's false because 35.2 is not in there, only integers are in there. So indeed, this does seem to work, and you can try it out with lots of different values and see that it correctly returns true or false, determines whether it's in there or not. So let's go back to this thing and finish up our analysis of this thing. So we want to know how long it takes to run this thing, and everything we analyzed before is still true. All of these lines here, they take constant time. They're just doing basic operations. And now, when we call bin search recursively, there's nothing fancy that we need to do to prepare the arguments for that. Those are just basic operations. A, I, M, X. Here we have to do a little bit of addition and subtraction to figure out the proper arguments, but there's nothing complicated there. It just takes constant time to prepare the arguments, but we are calling a function that's going to do some more work inside of it, so we have to figure out how long this is going to take. Okay. So let's see what this means, how we can analyze this. So let's say we'll call T of n, we'll say that equal the running time of bin search R with the argument n. So that's this argument here, which is actually the length of the array that you're searching on. Okay. So what do we know from our analysis? We know that T of n is less than or equal to, well, all of these O of 1s here. Add all of them up, and remember when we talked about this arithmetic using these big O's, you just keep the biggest thing in the sum. Well, here they're all the same, so we just keep one of them. So it takes a constant amount of work plus whatever time it takes to make a recursive call. So, or three things could happen. One is nothing. We actually find the element we're looking for in one step, in which case we just return true and we're done. In another case, we recurse on the first half of the array, the first m elements of the array. Otherwise, we recurse on n minus m minus 1 of the elements of the array. So what's m here? It's half the array, so it's half of n, right? And that means actually n minus m minus 1. So what I know here is that m is less than or equal to n over 2, the real n over 2, real division here. So even if n is odd, m is the integer division, so it's actually smaller than that. And here, n minus m minus 1, turns out that that's also less than or equal to n over 2. Whether n is odd or even doesn't matter. It'll be less than or equal to n over 2. Which means that if I'm looking at this running time here, I do all this constant amount of work, and then I have to call this function again, but with a new argument, a new value for n, and that new value for n is at most n over 2. Okay? So this is a way for me to write down what the running time is of this function on an array of length n. It's called a recurrence equation, and it says, well, the running time on an array of length n, that's at most constant plus the running time on an array of length n over 2. Okay. And now I'll do something a little bit funny. This constant is a little bit iffy here, so I'll write that in as c and say that this is for some constant c. And c, of course, has to be bigger than 0. You can't run in 0 time, and you can't run in negative time. All right, so that's interesting. This says sort of intuitively what we think. You start with an array of length n, you do a bit of work, and now you're searching on an array of length n over 2. Well, okay, so that's going to work recursively, and when I start searching on this array of length n over 2, what am I going to do? Well, I'm going to do a little bit of work, this constant amount of work, and then I'll be searching on an array whose length is half the size of that, which is n over 4. Okay. And for this array of length n over 4, I'm going to do a little bit of work, and then I'll be searching on an array whose size is half the size of that, which is an array of length n over 8. Right. Is this making sense to people? I'll start with an array of length n. The next one will have size at most n over 2, then at most n over 4, then at most n over 8. But this can't go on forever, because eventually I get down to an array of length 1, and then after that it's an array of length 0. So basically this just keeps going on for a while. And the number of times that it goes on is the number of times I can divide n by 2 before I get down to 1. So what's the name of that number? So how many times can I divide n by 2 before it becomes smaller than or equal to 1? Yep. Yeah. So that's the definition of the base 2 logarithm of n, more or less. It's just the number of times you can take n and divide it by 2 before you get a value that's less than 1. Okay. So this whole thing ends with a whole bunch of c's, c times log n of them, and then it just finishes there. It just stops at that point. So the running time, we started with this funny recursion relation or recurrence relation, and we solved it to c of log n. And now switching back to our big O notation, that's O of log n. Okay. So this is a very fast algorithm, and let's see why. How fast is it? Well, if we want to know, we can quickly write a Python program. Let's say. So I want to know how big this log n, what's log n look like. So let's make a short program that does a bunch of logarithms, and let's say for I in range 20. What we'll do is we'll print 10 to the I, and we'll also print log 10 to the I, and it's the base 2 logarithm that we want. Let's just convert that to an int. Math.log. Okay, so these are different values of n versus the logarithm of n. So when n is 1, log n is 0. When n is 10, log n is 3. So rather than looking through the whole array of length 10, we have to look at 3 different values before we find what we're looking for. It's probably 4. When it's 100, it's 6. When it's 1,000, it's 9. So now if we went looking through this array one element at a time, we'd be looking through 1,000 elements. Using binary search, we only actually have to look at 9 of them. Gets more exciting when we get up to, for example, here we're at 1,000,000, and the log of 1,000,000 is only 19. So if instead of using binary search, if we just asked is x in A, instead of doing this binary search thing, well, that would look at 1,000,000 array elements. Binary search will look at 19 array elements. And go down 3 more levels. Here we are looking at a billion, an array of size 1 billion. If we ask if x is in that array, it will have to look through 1 billion elements. Binary search will look at 29 of those before it finds out whether it's in there. So this is a lot faster. It's not completely independent of the value of n, but it certainly grows very, very slowly as a function of n. Okay. So so there you go. Now you know binary search, and that it's a little bit, it takes some work to implement, and you also have seen now that when you're trying to make efficient implementations of algorithms, at a very high level, you guys knew how binary search worked already before you started this course, because when we played this game, or at least some of you knew that the first thing you should look for if you're trying to guess a number between 1 and 1,000 is to guess 500. So you knew this binary search thing and sort of how it worked. But when you try and implement it, your first crack at it may not actually be efficient, because the obvious thing to do is to say, okay, after I check the middle of the array, I can either recurse on the first half or the second half, but that recursing, if you just take a slice, you'll slow down the whole algorithm. So, so you have to be careful there. As an exercise, you can try and write this code non-recursively without doing recursion. It's not hard to do either. Basically, a while loop that keeps track of the values of I and n will also work. Okay. So any questions about that? Yeah.
So if you were to ask us, how long does this take, would old log n be the answer?
Yeah. So if I said, what's the running time of this algorithm, I would probably have to tell you, specify it a little bit more, as a function of n, or or this first one up here would be as a function of the length of a. Then the answer would be the running time is order log n. That would be the best answer. Okay. So what I want to look at now is it'll be instructive to look at some sorting algorithms. Let me. I don't want this code to run every time we load this file. So I want to look at algorithms. So we've seen binary search now. If you give it a sorted array, it can very quickly test if something is in the array. So then the natural thing to do is to say, well, how do I sort? How do I get an array that's sorted? So let's try and sort of make up a really easy algorithm that hopefully will work for us. So it takes an array A and should sort it. So what's, I don't know, anything you could think of to sort an array by hand? So one thing is to just do this. Python has a built-in function called sorted. This will return a sorted version of A. Or if you really want to sort A and not copy of it, you can also just do that. But that's not very instructive for us. So let's try the most basic operation, which is we'll take some pair of elements. Let's say A at I and A at I plus 1. And basically, we'd just like to know if those two things are in the right order. So A at I and A at I plus 1 are in the right order if what? Yeah, so if A at I is less than or equal to A of I plus 1, that's the right order. So if it's bigger than A of I plus 1, then that's the wrong order. Swap them. Python is great for this. That's how you can swap two values in Python. You make a tuple and change the order of them. So that swaps them. Now, what if this, so this says, if I give you an index I and you look at I plus 1, you can determine if they're in the wrong order. So what if I look at every index I? So I could do something like for I in range, it would have to be range length of A minus 1. So not length of A, because we're going to also look at I plus 1 here. We'll do that. So that'll check if these two, if A at I and A at I plus 1 are in the wrong order, and it'll swap them. So is that going to sort the array? No? Okay, so let's see what it does. So we'll just print A after every step of this thing. Okay, so there's A, and let's try sort 1 of A. So that's what it did. There's the array at the beginning is the first line, and then it shows us after each step of this process of checking if A at I is bigger than A at I plus 1. So it first compared 7 and 3 and said, hey, 7's bigger than 3, let's swap their order. Next it compared 7 and 8 and said, they're okay, let's move on to the next thing. It compared 8 and 5 and said, hey, they're in the wrong order. Let's move on to so swap them, so now it's 5 and 8. Move on to the next thing. Now it's comparing 8 and 6. They're in the wrong order, so it swaps them. Now it's comparing, so 8 and 6 were in the wrong order. Now it's comparing 8 and 1. They're in the wrong order, so swap them. Now it's comparing 8 and 0. They're in the wrong order, so swap them. 8 and 4 are in the wrong order, so swap them. 8 and 9 are in the right order, but then 9 and 2 are in the wrong order, so swap them. So the result is not a sorted array. What can you say about the result? Even that's not true. So if it was true that every pair of consecutive elements were sorted, then actually the whole thing would be sorted. Because if A0 is less than A1, which is less than A2, which is less than A3, the whole thing would be sorted. So, and you can see counterexamples here. You still have 7 and 5 in the wrong order right beside each other. Yeah. Yeah. So one thing this thing does is it will put the last element in the right spot. And that's because as it goes along, when it swaps an element, you can think of it as picking up that element now. And it's actually going to pick up that element and keep moving it forward until it finds a bigger one. And there's only one element where it won't find a bigger one, and that's the biggest element in the array here. Okay, so for that reason, this thing is actually called bubble sort. Because after one pass through the array, the biggest element bubbles its way up to the top of the array, to the end of the array. Now, what if I did this again? What would happen? Yep. So if I do it again, 8 goes to the end. And now if I do it again, 7 ends up where it should be. And then 6, and then 5, 4, 3, 2, and the rest are already where they should be. Okay. So that says each time I do this, one element ends up where it should be, which means that I only have to do this for range. Certainly n times would be enough to make it work. Yes, length of A. So one thing I'll let you in on, whenever you talk about algorithms, people will start immediately referring to some variable called n. It always refers to however big the problem is. In this case, we're trying to sort an array. N means the length of A. You'll find me doing that all of the time. So implement bubble sort. Now, we don't want to print out the result of every swap. Maybe we'll just print out after each iteration what it looks like. And I should do import random give us an array to work with. Really? Okay, so there's our array A. If we call bubble sort on A, anybody see the problem? I didn't think so. Oh yes, it's because it crashed before it got to the definition of the function, this random shuffle business. So we have A, bubble sort A, there. So it starts out here. 9 actually happened to be right there at the end, but after the second iteration, then 8 is in the right place, and then 7 is in the right place, 6, 5, 4, 3, 2, 1, all the way down to sorted at the end. Okay. So there, we've implemented a sorting algorithm, and seems to work. Fantastic. So let's analyze it now. So what have we got here? We have 2 loops, one inside the other, and inside that loop is an if statement. Well, one thing I do know how to analyze is this part here, where you swap things. That only takes constant time. That's just taking a few values and reassigning them. This if statement, all it's doing is comparing 2 elements in an array. We saw that looking up values in an array is constant time, and comparisons are constant time, so this is also constant time. Now, this loop here, how many times, I mean, what's the number of times that this thing executes? Yeah. Yeah, so this thing executes the length of A times, and that means everything inside it executes that many times. Okay, so, and again, I'll say, remember, n is defined as the length of A. So this runs n times, or let's say has n iterations, which means that this thing here, or n minus 1, but close enough, this thing here also gets executed n minus times, n minus 1 times, and this thing here also gets executed n minus 1 times. But that's not it. There's still this outer loop here. We haven't accounted for that yet. All of this n minus 1 and n minus 1 business, that just accounts for one iteration of this thing. And this thing iterates n times. So this has n iterations and runs n times. Which means these inner guys here, they don't just execute n minus 1 times, but they execute an additional, multiply that by n. Okay, so if you multiply all of that out, you'll get n squared minus n. So you get something like n squared minus n. But remember this big O notation, we always keep the bigger, when we add up a bunch of big O things, we keep the biggest one. So what's bigger, n or n squared? N squared. So we'll just keep this n squared. So this this running time here is O of n squared. So this runs in O of n squared time. Okay. So n squared, is that one of these fast ones or not so fast? Not so fast. So we had a log table. Let's extend that a little bit to just a table, and maybe let's not go so big. I guess we could do that. 2 n log n. Let's put a n squared in there. And there I'll have to have something like 45 digits. No. So here's n versus log n versus n squared. When n is 1, not much difference there. But when you get up to, for example, n is 10,000, log n is 13, and n squared is 100 million. So if we use bubble sort on an array that contains 10,000 elements, it's going to end up doing 100 million of these comparison and swap operations, roughly. And it's going to get worse if we go as we get bigger. So if we increase this by a factor of 10, then the running time here is going to increase by a factor of 100. And we can check that out. So let's say A is equal to range. Let's take 1,000 elements. So it's pretty fast for 1,000 elements, 10,000 elements, not so fast. So 1,000 elements, there was actually a noticeable time that it took, so some fraction of a second, maybe a third of a second. Now it's going to take 100 times as long as that. So whatever, 100 times, it should maybe finish in a minute, but that's not so good. Okay, so there, it's finished. Compare that to the system sorting routine, which, well, which takes, no time at all for 10,000 elements. It certainly doesn't take nearly 60 seconds or anywhere near a second even. So the system sorting routine must be doing something faster. Well, let's try and do something, maybe another sorting algorithm which is a little bit faster. Well, no, let's skip to the good fast one. Let's try and implement a recursive sorting algorithm. So we've seen one already. We saw quicksort, and quicksort is great, and it's a fairly short to implement algorithm. Unfortunately for us, it's difficult to analyze. In fact, you will be depending on what you do, you'll either be well into your second year or maybe even into your fourth year before you're ready to analyze the running time of quicksort. So let's look at a different recursive sorting algorithm, which is one that we can get our heads around and really understand why it's efficient. And it's called merge sort. So it's a recursive sorting algorithm. We have an array A, and we would like to sort it. So if I wanted to do this recursively, I mean, the nice thing about recursion is it's almost like magic. You get to recursively call this thing on something that's smaller, and almost magically it comes back sorted. So, you know, if I say A0 equals merge sort, whatever you want, let's say A at 1 up till the end, then magically recursion will sort that for me. It'll come back, A0 is sorted, A sorted, everything except the last element. But I have different choices. I could sort everything except the first element, everything except the last element, or I could do other things. This idea of recursing on everything but the first element, we've done this before. It's what we tried when we were trying to find a recursive algorithm for adding up all the elements in an array. Did that work well for us? Yeah. So if you do that, you know, then basically, to sort an array of length n, first you recursively sort an array of length n minus 1, which then recursively sorts an array of length n minus 2, which recursively sorts an array of length n minus 3. And we saw, well, if you start out with n bigger than 1,000, this isn't going to work. And, and we're aiming for something that's efficient for n up to 1,000,000. So never mind efficiency, but it's not even, it's going to crash if n is bigger than 1,000 and we try this kind of thing. So what's a different strategy where you don't get, in fact we did the summing thing this way, where you don't get such a bad behavior. Yeah. Yeah. So you sort the first half like that. So this will recursively sort the first half of the elements, the first n over 2 of the elements. Well, that was so easy. Let's sort the second half too. So the second half is given by that. Wow, recursion is fantastic, right? I mean, look how good we're doing now. We've sorted the first half of the elements, we've sorted the second half of the elements. When we're doing recursion, we better look out for a base case. So what's a base case here? An array that's really easy to sort? Yeah. If the array is empty, then you can just return it, or return a new empty array, it doesn't matter. Otherwise, we split the array in two, and we sort the first half and we sort the second half. So now the picture is, you know, we can I don't want to print them because we don't have enough in place. So now the first half is sorted and the second half is sorted. So think of the array elements as people. Maybe you want to sort them by their, you know, alphabetically by their names. And so what I've done is I've taken half the people and put them in one group and said, go away and sort yourselves. So line up alphabetically by your names. And now I have another group, the second half, I sent them and said sort themselves. So they're lined up alphabetically by their names. So I have these two lines of people. They're standing, each line is sorted alphabetically by their names. And now what I want to do is merge them, put them together so that the whole thing is sorted alphabetically. Okay, so I want to do something like return, well, let's say merge A0 and A1 back into this array A. So let's even make it a little bit simpler than that. Not back into this array A, but into some empty, into some array with nothing in it. Let's call it B. So I have these two lines of people. Each line is itself sorted, and now I want to make this one line. We'll call it B of everybody in sorted order. So first thing I want to do is get the person whose name comes first in alphabetical order. So where would I find that person? So there's two lines of people are standing up. They're all sorted in each line is sorted in alphabetical order. Where's the one with the first smallest name? Yeah. I'll give you a chance. Yeah.
The first line, the first person in the first line.
First person in the first line always?
Well, A0.
Well, so I took these people and I just split them up arbitrarily and sent them to sort themselves off. So yeah, so it's either the first one in A0 or it's the first one in A1. So let's set this up and say I0 and I1. They're start out both being equal to 0, and then we'll say something like for I in, I see why I wanted to do that. So I'll start with three variables, I0, I1, and J. Why J? Let's stick with I. And here I'll say for something in the range length of A. So I want to repeatedly go through this process of picking something either from line 0 or something from line 1 and making that be the next thing in the next thing that I add. Okay. So a couple of little cases we have to look out for that show up near the end of this process. So one thing that can happen is that I0 is equal to the len of A0. So what does that mean? So I0 is supposed to be the next person in that line A0, but if I0 gets all the way equal to the length of A0, that means there's nothing left in A0. So that means the next person comes from A1, which we say A at I equals A1 at I1, I1 plus equals 1. Okay. So if there's nobody left in line 0, then I just take the next guy from line 1. Otherwise, if there's nobody left in line 1, then I just take the next guy from line 0. A0 at I0, I0 plus equals 1. there's somebody available in each line. There's somebody in line 0, there's somebody in line 1. I want to compare them. So if A0 at I0, that's the next guy in line 0, if he's smaller than the next guy in line 1, then I'll take from line 0. A0 at I0. 1. And then finally, if none of those cases occurs, I take the next guy from line 1. Okay, let's just double check our code. Here it's all 1s. Here it's all 0s. All 0s and all 1s. And then finally, I've added another thing to A, so I increase the value of I. Okay. So is that, yep?
Why is it for underscore I underscore in range length?
Because I want to do this length of A times, so I want to do this until A is full. So I need to count up to the length of A. Now why underscore? Usually use this when you have a loop that's a counter like this, and you never want to use the value of the counter. Okay. So, well, why the length of A? Oh, because A is the array we're trying to fill. So if this was called by merge sort, then A0, the length of A0 plus the length of A1, that's equal to the length of A. So we'll go until A is full, which coincidentally will happen to be at exactly the same time both A0 and A1 are empty. Okay. And now we can, if we like, we can return A. Okay, so let's see. Maximum recursion depth exceeded. If the length of A equals 0, return A. Otherwise, M equals the length of A. Let's say if the length of A is less than or equal to 1. Otherwise, if we have an array of length 1 and we try and split it into two parts, we get an array of length 1 and an array of length 0. We recurse again on the array of length 1, which gets split into two parts, and so on. So if the length of the array is 0 or 1, it's already sorted. We can just return it. There we go. So there we go. Merge sort correctly sorts that array, and it should also work for an array of length 1,000. Correctly sorts that as well. And so let's try it on an array of length 10,000. Shuffle it. It's a nice big messy array. We'll call merge sort. We don't want the result displayed, so we'll assign it to a variable. And there. Runs in a fraction of a second. What if we up the size from 10,000 up to 100,000? Still pretty quick. Takes a second, a little more than a second, but less than 2 seconds. Okay, so this seems to be a lot faster than bubble sort. Bubble sort on an array of length 100,000, it's just not going to end before this class ends, for example. So this is a fast algorithm. Now what we want to do is understand why it's fast. So what does it do? If we analyze it, well, we see that this takes only constant time, right? Checking if the length of A is less than or equal to 1, that only takes constant time. Same thing if we have to return A. Computing the length of A divided by 2, that's no problem. But here's something we'll have to deal with. Now, this merge algorithm, how long does it take? Well, to know that, we have to go through and look at this code. So here we set 3 variables to 0. So this takes constant time. Here we make a loop. And that executes the length of A times. And what about all the stuff inside the loop? It's all constant time, right? It's all basic comparisons, adding 1 to stuff, assigning values, nothing fancy. So everything in this loop constant time, but it executes n times because it's inside a loop that executes n times. So and we've just figured out that the running time for that is if A is of length n, is order n. It's a loop that executes n times, and each iteration takes constant time. Okay. So now we know how long this takes. But we're stuck. We have these 2 recursive calls here. So that's a little bit, looks tricky for us. And it is indeed a little tricky, but we can work our way through it. And because we've worked our way through something like this before. So let's fire up our we want a clean slate to work with, so we want to analyze what happens when you call merge sort and you give it an array of length n. So if we use our stack frame picture, you call merge sort and you give it an array A whose length is n. So it does a few things. It calls merge sort on an array whose length is about n over 2. It calls merge sort on another array whose length is about n over 2. And then it merges those 2 things. And that takes order n time. So the amount of work that we do here is order n, and that's just for the merging part. Now, in addition to that, so this is the stack frame for merge sort, it calls merge sort again on an array A whose length is what? N over 2. Once all that's done, so a bunch of stuff happens down on this side of the left side of the picture, it calls it again on the second half of the array, which is another array, A, whose length is n over 2. Okay. Now, let's focus on the left-hand side here. So, the left-hand side, again, makes these two recursive calls. And then once it's done making those two recursive calls, it merges their results. So we'll change this just slightly. Instead of O of n here, we'll say C times n. For some constant C, that's the cost of this merging here. And C, you could figure it out by looking at the code. It's, you know, you have this loop that executes n times, and this is what's inside the loop. So figure out what C is from that if you care. So this is also going to do some merging, but it's only creating an array of size n over 2. This one was creating an array of size n. This one's only creating an array of size n over 2. So it's only going to take time C of n over 2, or C times n over 2. Okay. And then all this recursion is going to happen over here on the left side. This is going to come back. This is going to recurse and do its thing over here. And then eventually this thing is going to have to do its merge, which is going to take time C times n over 2. Okay. And then back up to the top to put all this together. Okay. Are we okay so far? All right. So let's go one more level in this, what happens in all this recursion. At this level, this guy has two problems to solve. Each one is of size n over 4. And each one of them is going to have to do a merge at the end, which is going to produce an output of size n over 4. And that's going to it's going to take time C times n over 4. Over here, the same thing is going to happen. And this is going to take C times n over 4, C times n over 4. Okay. And this tree, we call it a tree, the recursion tree, you know, it goes down some number of levels. So it'll go down for a while. And eventually, it gets to these base cases here, where you have arrays of length 1 or of length 0. And then they just return. Okay. So you get down to the bottom here, and you get these things which are arrays of length, you know, length 1 here. And eventually, every one of those things, every element ends up somehow in its own little subproblem of size 1. So we actually know how many of these things there are at the bottom, at least the ones that are of size 1. There's exactly n of them, because each array element ends up somehow at some point by itself in an array. All right. So if we look at these levels here, you know, here's the level 0, here's level 1, here's level 2, 3, and so on. How many of these levels are we going to have? Yep. Log n. Because at each level, the size of the array gets decreased by a factor of 2, right? We start at level 0, the size of the array is n. At level 1, it's n over 2. At level 2, it's n over 4. If we did one more level, it would be n over 8, and and so on. So it keeps getting smaller by a factor of 2, which means that there's only log n levels. Okay, that's fine. There's log n levels. But now we want to know how long this takes to run, not how many levels there are in the recursion tree. It's good to know that there's log n levels. That means we won't blow the recursive stack, right? Because we can support a recursive stack of nearly 1,000 elements, and we saw that we can already be sorting billions of elements with a recursive stack of size 30 or so. So there's no issue there. So that's good, but that's not all we want to know. What we'd like to know is the total time that all of this takes. And so we need to know the time that's spent adding up. If we add up all of the time spent in all of these boxes, what does that add up to? Well, the trick there is to add up these boxes level by level. So here at level 0, there's one box, and the time that I spend there is C times n. It's just the time it takes to make that last output array. Here at level 1, there's 2 boxes, and the time that I spend there in each box is C times n over 2. So it's 2 times C times n over 2. Oh, but look, that's just C times n. Now what happens at level 4? Same thing. There's 4 boxes. So 4 times I'll have to run this merge algorithm to produce a sorted array, but it's only a sorted array of length n over 4 each time. And so look at that. That's only C times n also. And the next one is going to be 8 times C times n over 8 equal to C times n. And if we go all the way down to the bottom here, it's actually n times, we can think of this as n times C times n over n. So n over n is just 1, n times C times that is just, again, C times n. So we added everything up level by level. We know that every level adds up to C times n, and we know there's log n levels. So if we add all of those up, sum all that, this is just C times n times log n, which is O of n log n. So merge sort is an algorithm whose running time is O of n log n. So n log n, how does that compare to everything else? So we've seen running times of log n for binary search. We've seen running times of n for anything that does a simple loop. And we've seen running times of n squared. So where does n log n fit in there? Is it bigger than log n? Yeah, it's bigger than log n because it's actually log n times n, so it's bigger than log n. Is it bigger than n? Yep, it's bigger than n because it's n times log n, and log n is bigger than 1. Is it bigger than n squared? No. And why is it not bigger than n squared? Well, that's because we figured out a long time ago that log n is somehow way smaller than n, and n squared, well, that's just n times n, and so that must mean, let's do it the other way. So that must mean that n log n is way smaller than n times n, because log n is way smaller than n, right? Just hide these n's here, and you're back up to this equation up here. And indeed, we ran this thing, and we saw that it can sort hundreds of thousands of elements in a second or so. And we can extend this table a little bit more to give us show us what n log n looks like, and this is just n times So there you go. There's those tables for you. N log n is not really getting bigger much faster than n, right? Even when n is up here, which is like 10 to the 20, well, it's only n times 63. It's not huge, unlike this thing, which is enormous. So n log n somehow fits in between these two nicely. It's not much bigger than n. And that's why this is such a fast algorithm.